Hold a peanut in your hand. That's the size of it. That single object, no larger than what you'd find in a shell, holds enough energy to power your home for an entire year. Not for a month, not for a season, for 12 full months. It's a uranium fuel pellet, one of thousands that sit at the heart of nuclear reactors across the globe. And if you've ever wondered how something so small can contain so much power, if you've ever asked yourself what goes into creating one of the most dangerous materials on Earth, and then transforming it into clean electricity that powers cities, then you're about to witness a journey that begins beneath the frozen ground of Saskatchewan and ends inside the most precisely engineered machines humanity has ever created. This is the story of how we pull uranium from the Earth, how we separate what matters from what doesn't, and how we turn something capable of destroying civilization into something that powers it. Stay with me because this process will change how you think about the energy flowing through your walls right now. The story of uranium doesn't begin with weapons. It doesn't begin with power plants. It begins with curiosity. A German chemist named Martin Heinrich Klaproth was experimenting with a black mineral sample. He had no idea he was discovering something that would reshape human civilization. He called it uranium, after the planet Uranus. For over a century, uranium sat in the periodic table as just another element. Interesting, heavy, completely unremarkable. Then came 1896. A French physicist named Henri Becquerel was studying uranium's properties. He left a uranium sample on top of a photographic plate. When he developed the plate days later, it showed an image, a shadow, cast by the uranium itself. The element was emitting radiation, without any external energy source, without any chemical reaction. The uranium was radiating on its own. That single observation changed everything because it revealed a fundamental truth about the universe. Matter itself could release energy just by existing. This discovery sparked a frenzy of scientific investigation. Marie and Pierre Curie isolated other radioactive elements. James Chadwick discovered the neutron, the subatomic particle that would become the key to unlocking nuclear power. And then in 1938, German chemists Otto Hahn and Fritz Strassmann demonstrated something extraordinary. They took uranium-235, a rare isotope hidden inside natural uranium, and struck it with a neutron. The atoms split apart, and in that splitting, it released not just energy, it released more neutrons, which could strike other atoms, creating a chain reaction, an exponential release of energy that could only be stopped by controlling the reaction itself. They called it nuclear fission, and they had no idea what they had just made possible. Here's the fundamental challenge that defines everything that comes next. Natural uranium is 99.3% uranium-238, a heavy isotope that does not readily undergo fission. Uranium that just sits there, stable, inert, useless for creating a chain reaction. The remaining 0.7% uranium-235 is the reactive isotope, the one that splits when struck by neutrons, the one that releases energy, the one that matters. So if you want to create nuclear power, you face an immediate problem. In natural uranium, the useful isotope is buried in a sea of the useless one. For every atom of U-235, there are 142 atoms of U-238 getting in the way. To create electricity in a reactor, you need to increase that proportion, not dramatically, but deliberately. A modern nuclear power plant needs uranium enriched to between 3% and 5% U-235, an increase from 0.7% to 5%, 7 times more concentrated. But here's what makes uranium genuinely terrifying. Weapons-grade uranium, the kind used in atomic bombs, requires enrichment above 90%. The same technology, the same process, the same equipment, just turned up to a different setting, which is why nuclear enrichment is one of the most carefully monitored and heavily restricted technologies on the planet. Because the line between powering cities and building bombs is not a different process, it's just a matter of degree. During World War II, the United States understood this danger before anyone else, and it mounted one of the most ambitious scientific projects in human history, The Manhattan Project, led by figures like Enrico Fermi and Robert Oppenheimer, the brightest scientific minds of the era, were tasked with one goal: develop the technology to enrich uranium rapidly. At massive scale, they invented two enrichment methods: gaseous diffusion and high-speed centrifuges. The centrifuge method was revolutionary. It exploited a fundamental fact about physics. Atoms of different mass, when spun at extreme speed, separate based on their weight. U-235 is fractionally lighter than U-238, by a margin so small it's almost immeasurable. But spin them fast enough, and that tiny difference becomes the difference between what settles at the center and what drifts toward the edge. By August 1945, the Manhattan Project had succeeded. They produced enough enriched uranium-235 to create the little boy atomic bomb, dropped on Hiroshima. A single bomb, powered by enriched uranium, destroyed an entire city. In that moment, the world learned what enriched uranium could do, and the question immediately shifted. Not, can we make bombs, but can we control this technology for peaceful purposes? The story now shifts from laboratories to the Earth itself, because uranium enrichment starts long before any centrifuge. It starts with mining. 3 countries account for 60% of global uranium production: Australia, Kazakhstan, Canada. But there is one location on Earth where uranium occurs in higher concentrations than anywhere else: the Athabasca Basin in Saskatchewan, Canada. In most places, uranium deposits contain 0.1% to 2% uranium. In Saskatchewan, the concentration reaches 15% to 20%, up to 100 times richer than the global average. But this richness comes with a problem. Above the uranium ore lies something else: a thick layer of sandstone, completely saturated with groundwater, water that would flood any conventional mining operation. So the engineers faced a choice: either abandon the deposit or invent a completely new way to extract it. They chose innovation: artificial ground freezing. The process sounds simple, but it's engineering at an extraordinary level. Drill bits tipped with tungsten carbide bore through the rock and install a network of cooling pipes. These pipes carry calcium chloride brine, chilled to -22 degrees Fahrenheit. This sub-zero liquid flows through the sandstone's pores, freezes the water trapped inside, turns the porous rock into solid ice, creates an impermeable frozen barrier that isolates the uranium ore below from the groundwater above. Installing these pipes takes up to 8 days per pipe. The full system requires 200 of them. Once the frozen wall is in place, extraction can begin. A pilot hole guides larger drilling equipment to the ore body. A reamer drill widens the shaft, breaks the ore apart, sends fragmented rock tumbling into collection chambers below. The entire operation is remote controlled. Workers never descend into the mine, never risk cave-ins, never risk radioactive exposure. Fresh air is circulated every 20 minutes through ventilation systems. Once brought to the surface, the ore passes through radioactivity scanners, confirming uranium content, typically between 15% and 18%. Exceptionally high quality. This ore, so rich in uranium, is then crushed, ground into fine sand, mixed with water to form a slurry, pumped to the surface, and hauled by specialized trucks to a processing mill nearby. At the mill, the chemical transformation begins. The slurry is treated with acid, a controlled chemical reaction that selectively dissolves the uranium while leaving other minerals to settle at the bottom of the tanks. The uranium-bearing solution is drawn off, purified through a series of additional chemical reactions. Then it is heated to 1560 degrees Fahrenheit. At this extreme temperature, uranium transforms. It becomes uranium hexafluoride gas, a compound that will allow the isotopes to be separated. The hexafluoride gas is fed into high-speed centrifuges, industrial machines spinning at velocities so extreme that the g-forces inside are thousands of times stronger than Earth's gravity. Inside the rotor, something remarkable happens. The slight mass difference between uranium-235 and uranium-238, a difference of just 3 atomic mass units out of 235, becomes significant under those extreme conditions. Uranium-235, being fractionally lighter, concentrates toward the center of the rotor, where it can be separated. Uranium-238 drifts toward the outer edges. The result is a separation so precise that enriched uranium gradually accumulates in one stream, while depleted uranium accumulates in another. The enriched product is converted into a dense, dark powder, packed into sealed 55-gallon steel drums, clearly labeled with radioactive hazard warnings. These drums are then shipped to a nuclear fuel manufacturing facility, where the transformation from ore to electricity enters its final phase. At the fuel manufacturing plant, uranium undergoes further transformations, moving between different oxide forms, undergoing additional purification, until it becomes uranium dioxide powder, with precisely the right properties for what comes next. The powder is fed into machines that apply several tons of hydraulic pressure, compacting it into small cylindrical pellets, roughly the size of a peanut. This is where the energy density becomes tangible. A single pellet holds the energy equivalent of 1,800 pounds of coal, or roughly 150 gallons of oil. That peanut-sized object represents the energy that would fill a coal car that's 150 feet long. The pellets are loaded into industrial furnaces, centered for 24 hours at extreme temperatures. This process eliminates internal pores, increases the material's density, dramatically improves structural stability. After the furnace, robotic arms take over, with mechanical precision. They stack 30 pellets inside zirconium tubes. Zirconium was chosen for a very specific reason. It's exceptionally resistant to heat and corrosion, but critically, it allows neutrons to pass through freely during the fission reaction. The tubes are sealed by automated welding, creating finished fuel rods. 37 fuel rods are then bundled together into a structured fuel assembly. This assembly is weighed with extreme precision to verify the exact uranium content, down to the gram. The radioactivity emitted by these assemblies is low enough that workers in proper protective gear can handle them safely. But it's enough that every movement is tracked, every assembly is documented, every specification is verified. Once delivered to a nuclear power plant, these fuel assemblies are loaded into the reactor core, a cylindrical chamber that holds up to 5,760 fuel rods distributed across 480 fuel channels. And this is where the entire journey culminates, where all the mining, all the chemical processing, all the isotope separation, all the manufacturing precision comes together for a single purpose: creating fission. Fission begins when neutrons collide with uranium-235 atoms. The collision is violent, the atom splits, and in that split, it releases three things: enormous amounts of heat, radiation, and additional neutrons. Those additional neutrons strike other uranium-235 atoms, which split and release more neutrons, which strike more atoms, which release more neutrons. It's a chain reaction, self-sustaining, exponential, generating immense heat measured in hundreds of degrees. This is where the danger becomes most acute, because an uncontrolled chain reaction is what you want to happen in a bomb. But in a reactor, you need control. The reactor itself is encased in 6-ton thick reinforced concrete walls. Control rods, made of materials that absorb neutrons, are inserted into the fuel assemblies. Adjusting their depth raises or lowers the reaction rate. Automated safety systems continuously monitor temperature, pressure, neutron flux. If any parameter reaches critical threshold, the reactor shuts down automatically, not gradually, immediately. The heat produced by the controlled fission converts water into steam, massive amounts of steam. This steam drives turbines housed in buildings 1,300 feet long, as tall as 20 stories. Spinning at 100 revolutions per minute, each turbine drives a generator capable of producing more than 750 megawatts of electricity, enough to meet the energy needs of 500,000 people, produced without carbon emissions, without air pollution, without the mining scars that coal requires. This is the power of a peanut, multiplied across thousands of pellets, across hundreds of fuel rods, across massive assemblies, across entire reactor cores, converting the energy locked in atoms into the electricity that flows through your walls. But the journey doesn't end when the electricity is generated, because after roughly 1 year of operation in the reactor, the fuel assemblies are spent. The uranium-235 is depleted, the chain reaction slows, the fuel can no longer sustain the power generation needed. At this point, the spent fuel is removed. But it's not over. In fact, the danger intensifies. The spent fuel is so intensely hot and so intensely radioactive that it cannot be touched, cannot be transported normally, cannot even be stored in conventional ways. It must be immediately submerged in cooling pools 26 feet deep, filled with purified water. The water absorbs the heat, prevents meltdown, shields workers from radiation, and it must stay submerged. Not for days, not for months, for at least 10 years. Sometimes for decades. More than 700,000 spent fuel rods currently rest at the bottom of these pools at nuclear facilities around the world. Each one represents the energy that powered thousands of homes. And the lingering question, what happens to them next? Some nations reprocess spent fuel, extracting remaining uranium and plutonium, creating new fuel, reducing waste volume. Other nations store it long-term in specialized facilities, deep underground, designed to remain intact for hundreds of thousands of years. The technology exists. The process is proven, but the political will to implement permanent solutions remains one of the most contentious issues in energy policy. Silosing Segreman, the complete cyclate, 13, 15, 14. From the frozen ground of Saskatchewan, to the control rooms of nuclear power plants, to the cooling pools of spent fuel storage, you have now witnessed the complete journey. A journey that transforms ore in the earth into electricity in your home. A journey that began with scientific curiosity in 1789, when a chemist named Klaproth discovered an element. A journey that accelerated in 1938, when physicists learned that atoms could split. And a journey that continues today, with 10% of the world's electricity coming from uranium fission. The uranium pellet the size of a peanut, powering thousands of homes for an entire year, represents centuries of human ingenuity, decades of engineering innovation, and an ongoing balance between harnessing atomic energy for peaceful purposes while preventing the technology from becoming the most dangerous weapon civilization has ever created. This is the process that powers the modern world. This is enriched uranium, and now you know exactly how it's made.